In today's lecture, we'll be talking about liquid level sensors. So we will see how to measure a liquid level in a tank. And by liquid level, we will be talking also about liquids, but also about solids, so that we are able to measure the liquid level, for example, in a silo. Let me just divide the liquid level sensors into two groups. The first group will be called continuous sensors or continuous measurements. And in this group of sensors, we will be able to get continuously the distance. So the sensor measures the distance between the sensor and between the liquid level, and gives us a continuous info about this distance. So this distance is then measured, and we have it available either as an analog signal, voltage or current, or we may read it on some digital bus as a number. The second group of sensors for liquid level will be so-called point level detection. And this is very similar to proximity sensors that we know from position sensors. And point level sensors will give us the info that the liquid level is at the given distance where the sensor is installed, but we will not be able to read how much liquid is above our sensor. So we can use point level sensors, for example, to detect if our tank is full or if it is empty, but we are not able to read if it's not empty but not full, how much liquid do we have in the tank. The output signal of our point level sensor is 0 or 1. So it is a logic signal that is telling us yes, the liquid is there, or no, the liquid is not there. On the picture you can see that some of the principles that we will discuss are fine for both types of measurements. So for example, you can see that in the point level group we have capacitance, but we have capacitance also in the continuous measurement. So this means that it is possible to detect with capacitance both continuous level and point level as well. And you can see that the principles will vary a little bit if it will be a liquid or if it will be a solid. But again, we can see the capacitance here. So capacitance will be very universal principle also for liquid level. And we can see other principles as well. So for example, we'll be discussing the vibronic principle, and this is specifically a sensor for point level detection. On the other hand, if you see, for example, radar or ultrasonic, then this is a typical example of continuous measurement. And you can see it again here in both groups, so it is able to measure a liquid or it is able to measure a solid as well. So you will see that many principles are universal, and we may use that for liquid level, or we may use that for solid level. Here on this picture we can see an overview of some selected methods how we can actually measure some liquid level in a tank. And we will discuss only some of them. So on the left hand side you can see so-called magnetic level gauge. This is nothing else than a simple tube that is connected in parallel to our tank. So we have one connection here and one connection there, and if the liquid level is rising or in the tank, then the liquid level in the tube has to be the same as the liquid level in the tank, so it will be approximately here. And then this is a float, and we detect the position of the float. So you will see that in liquid level measurement in many cases we take the liquid level and we use some kind of position sensor to detect what is the position level. So here we measure the position of a float with a position sensor, which in this case it's based on magnetic, so it's called magnetic level gauge. So this is a continuous measurement. On the other hand, you can see here on the right hand side we have a float switch, and a float switch is a typical example of a point level detection. You can see how this is connected. It is again connected with some short pipes from the tank, so here and here. And if the liquid level is in this range, at some point where the float will start to rise, it will turn on some magnetic switch. So this is a signal 0 or 1 that is telling us the tank is full, and for example we will stop a pump so that we do not overfill the tank. You can see similar point level sensors here on the right side. So we'll be talking only about vibrating fork today, and you can see that it's possible to measure it with many other ways, so I've just selected the one. And on top of the tank we can see the continuous sensors. So we can see the ultrasound, we can see the radar, and then two other principles. One is called magnetostrictive. This is also one continuous measurement, but this is based on magnetic properties of a rod that is inserted in the liquid level tank. And here we have something similar to the radar, but the radar is using an antenna on top, but this transmitter has a rod that is submerged, and we measure the time delay and the different properties of the gas above the liquid level and of the liquid level itself. So out from those four, I have selected only the ultrasound and the radar as our examples. Now I have many links for quite interesting videos in the presentation. I will upload the presentation after the lecture to Moodle, so you can take a look on those videos. I highly recommend that because they are quite interesting. Let me start by explaining why the liquid level measurement can be difficult in some cases. So first of all, it's not a problem at all to measure liquid level if you have a tank with straight liquid level, you have a horizontal liquid level. You're not mixing anything, you don't have any armatures there, you don't have any protrusions from the tanks that would be there for, let's say, technological reasons such as temperature measurements and so on. So in this case, of course, it's not a problem to measure a liquid level. Basically any principle can be used in this case. Now we start to have a problem when we need to have mixing. For example, we are mixing two chemicals, and without an active mixing they would not mix properly. So we add a mixer in the tank so that will agitate the liquid. But at this moment, if we install a liquid level sensor, where should it be installed? So should it be here so that I measure this level, or should it be here so that I measure this level? Of course this shape is correct, but the size of this change in liquid level is exaggerated. In real liquids, of course, it's not like this, but this is to show you that if I add mixing, then suddenly I don't know where should I measure the liquid level, because the point in measurement of liquid is, in this case, is that I try to estimate where the liquid would be if the mixing would be off. So you see that it might be quite a problem, because I may need to install the sensor, and of course then the data, if I for example install it here or here at the edge, then of course the liquid level that I measure will also be a function of the speed of my mixer. So in some cases this might be a problem as well. Then we can start adding more properties of our liquids. So no problem at all if we have a steady liquid level, but we may have bubbles there. So for example, if we have bubbles, then if we use ultrasound, then the bubbles may prevent the ultrasound to propagate properly through our liquid. So bubbles may block, for example, ultrasound. Then some liquids may have foam on top of it. So if on the other hand we take ultrasound and install it from the top like this, then the ultrasound will be blocked on the foam and we'll be not able to measure with ultrasound again. But other principles will have trouble as well. Then we may have vapors, and again vapors will have different properties than the gas or the air around our liquid level, and they may change the propagation of radio waves, of ultrasound, and so on. It might be also an aggressive liquid or aggressive vapors, so we may have to protect the sensor from this chemical damage. For example, it needs to have an antenna if it's a radar that's made from stainless steel. On the bottom of the tank we can have some sediments. So if we have a sediment and we install a sensor from the bottom, such as for example a pressure sensor on the bottom, it may get blocked by the sediments. Then we may add high temperature. So we may have a liquid that has quite high temperatures that would be able to destroy our temperature, the pressure sensor or any kind of liquid level sensor that we have directly submerged into our liquid. High pressure, that's the same problem. We may add some corrosive materials such as acids, for example. We may need to measure some radioactive material. So then at the end we may find that it's either very difficult to measure liquid level, or that with current technology it might be even impossible. Because if you add all those properties together, then you find that there is probably not a sensor that would satisfy all those conditions, or it will be so expensive that you will have to pay a lot for the sensor, or will have a problem with reliability, for example. So in some cases we have a trouble to find a suitable sensor for liquid level. How about solids? Well, in solids it can be difficult as well, and here you see two reasons why it can be so. If you have a solid in a silo, then it may form multiple peaks. So as you are filling, for example, from the top the silo, you expect that it will do something like this, like a hill. But based on the properties of your solid, it may do, for example, multiple peaks. Or if you have like really large like particles like stones, for example, then it may form some openings. So even if you measure the liquid level, you say, okay, now my silo has this liquid level, for example, then you cannot calculate correctly the volume because of those openings. And if you measure only one peak, then you don't know, okay, there is another peak there, there is some hollow space here, there's some hollow space there. So the safest way here, if it's possible, would probably be to weight the entire tank, and then you get the weight of your solid. So again, it might be difficult to measure solid in liquid solid level in some tanks. Another problem is the interface. Here, sorry, I forgot the Czech tags. So this should be interface, and the problem is that many liquids, they are mixed with something. For example, if you have a mixture of water and let's say oil, then you will have one liquid sitting on the bottom, you will have another liquid sitting on the top, and somewhere between that you will have the interface. And you may be interested into measuring the interface, because you want to know, for example, how much oil is there or how much water is there. Well, inverse, the water will be on the bottom, and there will be special sensors for this, especially the capacitive combined with the radar can give you info about the interface and about the two liquid levels as well. Plus, of course, you may have the foam on top. So now the question is, where actually is your liquid level? Is it here where you have the foam, or is it somewhere here where you have the oil, or is it somewhere here where you have the interface between water and oil? So this actually depends on what do you need to measure, but again, this might be quite complicated to measure, let's say reliably, because you may need to do this automatically and make some decisions in your control systems based on this. And of course, you can have an emulsion, which is the mixture of those two liquids together, and then it might be completely impossible to measure what it's doing. So here you can see a very brief comparison between the types of sensors, and between how difficult that is, and if it's possible or impossible, and also how expensive this will be. So if we start from let's say low pressure here, such as around atmospheric pressure, then let's take water as an example, then it turns out that this is quite easy, and you may use all sensors that you find, basically. So you can use mechanical, capacitive, ultrasound, and so on. Then as our pressure keeps increasing and we are changing the types of liquids, then it gets more difficult and more costly. So for example, at the let's say farther end here, we may have some very hot or even maybe even very cold liquids, such as cryogenic liquids. We may have vessels or tanks with internal structures that are there, for example, for rigidity. And we may have high temperatures, we may have high pressures. So at this point it may be nearly impossible to measure the liquid level. So we need to use, for example, a radar or a nuclear level meter, which compared to the very simple case we had on the first place will be quite expensive. So there will be a very large range of different types of liquid level sensors, and they will vary in all those properties. So it's very variable based on the conditions that you actually have in your experiment. Why is it important to measure liquid level precisely? Well, because first of all, your process may depend on that. You may need to measure and then mix a very specific amount of products. So you're mixing some liquids or you're mixing some solid into a liquid. You are looking for some specific chemical reaction, for example, and you have a recipe for that, and you need to know what is the liquid level so that you can get the volume of your liquid. So let's say we have an example of a very large tank, I've chosen for no reason at all, say 20 meters the diameter. And now what is my area? So the area we can calculate, and it's like 314 square meters, so quite large volume. And imagine that we have some kind of sensor either on top or on the bottom that is able to give me continuously what is the liquid level. So I measure, for example, this distance, and let's say that my measurement error is only 10 millimeters. So you would say, okay, I have 20-meter tanks and I have 1 centimeter of error in the measurement. But if you transfer this to volume, then it will give you approximately 3 cube meters. So this might be also quite expensive liquid, and that if you don't know if you have more than 3 cube meters or less than 3 cube meters, that might be a problem also if you want to sell it, for example. So we will see that many liquid level meters are able to measure within few millimeters of accuracy. So we are trying to achieve very high accuracy. Because of this, if we have a large diameter of our tank, then we may have a big error in the calculated volume. Okay, so let me start with the first group of sensors, which will be continuous measurement. But you will see that in many cases this will also overlap into the point level. So the first the first possibility that you could actually think of how you measure the liquid level is to use a pressure sensor. So we can install a pressure sensor at the bottom of our tank, and we can measure the hydrostatic pressure. So we know that the hydrostatic pressure is equal to the liquid level times density of my liquid times gravitational acceleration. So this is a very known equation from fluid mechanics, and we can use this, and we can measure the pressure at the bottom of the tank. Now in my picture here I have it as an example of a well type manometer, but this is only an example. Of course you may use any kind of pressure sensor, for example the diaphragm with capacitive sensing that you place on the bottom of the sensor of the tank. You can do this in an open tank, so then you measure versus the barometric pressure, so the, let's say, ambient pressure that's around it, and you can do exactly the same as also in the pressurized tank. So on this right picture you see such an example. This is the pressure sensor, but if we have a pressurized tank, we are not looking for the pressure in the tank, we are looking for the pressure difference above and below the liquid level, so at the top and at the bottom of the tank. So here, again, only as an example, I have a U-tube manometer, but you would probably use something else, such as again, that pressure difference sensor based on capacitive sensing. And you see we have one tube from the bottom of the tank and one tube from the top, so that we measure the pressure difference, and this pressure difference is then proportional to our liquid level that we have in the tank. So it's quite easy to do it with pressure sensors. Here you see two examples of those pressure sensors. In this case both are absolute pressure sensors, so you see only one input port. So here and here we have those input ports, and we measure the typically deformation of some diaphragm. So you can see here what's inside. This diaphragm gets deformed if you increase the pressure, and then this is transferred through this rod to a position sensor. So this might be continuous reading, or if you have only the desire to measure like a liquid level, point liquid level, then you may set, for example, an end switch that will detect the change of position in this example. Here are a few more examples. It is very typical that those sensors are submerged into the liquid. So you don't need to drill any hole from the bottom, which might also damage the tank, and you may have a problem with leaking, for example. So those pressure sensors in many cases are submerged from the top. So it's like a long cable or a rope or some long rod. You can see here many examples, typical cables, but this is like a stainless steel rod. And you install this probe at the very bottom. It has the pressure input from the bottom, so it's over there. And typically there is a capacitive diaphragm sitting somewhere here, and you measure the deformation with capacitive changes. Quite often the diaphragm is made from ceramics, so that it is very resistant to corrosion, and you may submerge that even in aggressive liquids. The rest of the sensor is either from plastic, as you can see here, or it is made from stainless steel, again due to corrosion prevention. So it's quite easy to do that, but obviously it will not work for all kinds of liquids. For example, if we have a liquid with sediments, then it might be a problem, because if the sediment is above our sensor, if this would be the sediment and this would be the liquid, then obviously we will not be able to measure the liquid level, because the sensor would be blocked by the sediments. So this kind of liquid level meter is not suitable for liquids or for applications where we have many sediments, because of those reasons. On the other hand, it does not have any problem with bubbles, and it does not have any problem with foam, because we measure at the bottom, and the bubbles will go up, and the foam will also be up, and we don't care in this kind of sensor. Few more examples. Here you can see the input ports inside, so it's just like a body from stainless steel. Of course it's hermetically sealed, and the liquid may get into the sensor with those holes in the middle. There are more of them, but yeah, you can imagine that they might be blocked if you have some sediments that will prevent the liquid to enter into the sensor itself. So what can you expect? It's a pressure sensor, so it measures up to quite high temperatures and pressures, so approximately up to 400 centigrades and about 400 bars. Again, it may vary based on manufacturer and application, but this is like a rule of thumb example. So it will definitely not be measuring up to, I don't know, 1000 centigrades, for example, but up to a few hundreds of centigrades. And it is unaffected by the surface foam that is floating there, or by some bubbles that you may have in the liquid. Now, on the second example that I will give you as a sensor is, on the other hand, it's also a pressure sensor, but it combines the pressure sensing with the flow sensor and with compressed air. And this sensor is called a bubbler, or also a pneumatic liquid level meter. And this type of sensor has a huge advantage. And the huge advantage is that the only part that is in contact with your liquid is a tube. And we can make this tube from any material that will work with our liquid. So it can be ceramics, it can be stainless steel, it can be any other material that will not be destroyed with your liquid. And as far as you are running a continuous supply of compressed air, the sensor will not be blocked at any time. So it is also very reliable. Now, how does it work? We have a tube that is submerged in our tank all the way up to the bottom, almost. And we are blowing compressed air into our liquid. So here is a source compressor and we're blowing compressed air. And here it will escape as bubbles. Now what we can do is we can get the hydrostatic pressure at the end of our tube. It will be, I will call it H1, but it will be general. It will be some height, and it is obvious that if I have a constant pressure, then the flow rate will be proportional to my liquid level H. Because if my tank ends here, I will need lower pressure so that I have some flow of air. If my tube will end somewhere here, I will need another pressure so that I have some flow. So there will definitely be some dependence between the pressure that I measure and between the flow rate. So what we are doing here is that this is a flow sensor, but it will be also a flow regulator. So here on this flow regulator we will set a constant flow, and then if we have a constant flow that is maintained, of course, by changing the pressure, it means that this pressure P has to be proportional to my liquid level H1 that I measure. And as the liquid level will change, for example, if it will be here, I'm maintaining a constant flow, but I will need less pressure to have the same flow rate, same bubbles in my liquid. So we have a pressure sensor, and we have a flow sensor and a flow regulator. You can see the equation here. It's basically this is the liquid level. So again, density times gravitational acceleration times my liquid level, plus delta P2, which is the pressure of difference on the flow regulator that we have here. Because we will find out that the steady state response looks like this. Here we'll have the liquid level H1, and here will be our pressure, and it will be linear dependence that we see here based on this equation. So it will look, for example, like that, but the parameter of the line will be some value of Q. So if we have some specific value of Q, we'll have some dependence like that. Then if I have a larger flow rate, this will be Q2, this will be Q1, then for a larger flow we will have a larger value of the pressure drop on the regulator. So it will be shifted upwards, but it will have the same slope. So that's the reason why we need to keep the constant flow, and why we need to maintain this flow on some specified constant level. You can see that this will probably again not work for all cases of our liquids. So first of all, the liquid needs to tolerate the presence of bubbles, and you also need to have some source of constant pressure and flow from some compressor. So in time this might be quite expensive, because you need to supply the compressed air. And if your liquid will not tolerate the presence of bubbles, you cannot use this principle. For example, if this would be a tank with beer, then the customer would probably not be very happy if you measure the liquid level by blowing constantly the air into your beer. So it's not like a good idea to use that in those cases. Here you can see some example how this bubbler looks like. So what do we have here? Here this is the flow regulator. So we have a supply of compressed air that's going in. This will provide us some constant airflow that we can set. Of course, we see some valves that we have there to close the system. This would be going into the tank, and this is a pressure sensor. So you can see that in this case it's like a liquid level manometer, and this would be the pressure sensor, so that we can get some electric signal on the output and control and connect this to a control system. So this system, this so-called bubbler, is composed from a flow sensor and flow regulator and from a pressure sensor. We have seen both on the previous lectures how to do that, so it should be fairly obvious how this device is built. Now the third principle that I will explain you today will be very universal, and we will see it again and again also in the point level detection, and that's the capacitive liquid level meter. Now this meter can measure either a conductive liquid, or it can also measure a liquid that is not conductive. You can see both in my pictures, but in both cases this is acting like a capacitor. So we measure the capacity between two electrodes, and one electrode is in the middle of my tank, here the red rectangle, and since this is a tank, I am using the tank as the second electrode. So let's start with the case where our liquid is not conductive. That's the one on the left. So I have one electrode in the middle, I have one electrode as the tank. Of course, in this case the tank needs to be conductive as well. So if it's like a metallic tank, then I can use it directly. If it's not a metallic tank, if it's not conductive, I need to use two electrodes, and I will need to submerge them both into my liquid. And in here we see a capacitor. So here this is one electrode, this is another one. So here there will be some capacity. This is a cylindrical tank typically, so there will be another capacity like this. So like this is like a cross-sectional view. But we can see that the capacity of this part will depend on the dimensions, and it will depend on the material. So the material is described with permittivity, epsilon r, relative permittivity. If it's air, then it's very, very close to 1. It's like 1.000 and then something. So it's like mostly air. And here we have our liquid level, and it needs to have a different permittivity. So epsilon r1 needs to be significantly different than epsilon r2. So for example, if epsilon r2 would be air, would be 1, then if we have some liquid that will have epsilon r2, well, epsilon r1 equal to 2, then it might be impossible to use this principle. We need that our liquid has significantly different relative permittivity from the gas that's above it. Fortunately, for example, if we have water, then water has permittivity about 80. Depends on the temperature, of course, but approximately 80 for 20 centigrades. And then we have a significant difference between those two capacities. So as we are increasing the liquid level, our capacity that we measure is increasing. So C1 is increasing. C2 is decreasing, but C2 is very small compared to C1 because here we have different permittivity. And we will have also some constant capacity that I am calling C0, which can be the capacity of the cables, of the connectors, of the holders in your electrodes system as well. So C0 is the constant part, and it's typically quite small. It can be in few picofarads. So we are looking for the changes of capacity. Basically, capacity, regardless of the configuration, capacity depends on the cross-section, directly proportional. It depends on the distance between the electrodes, so this is inversely proportional, and then it depends on the material. And even if we have like a cylindrical capacitor, this is valid, although it's not in this form of the equation, but you will see in a minute how this looks like. So this is the simplest case when your liquid is not conductive. It gets a little bit more difficult when you have a conductive liquid. And by the way, water is also a conductive liquid. Although the conductivity is very small, for capacitive measurements you need to consider it as a conductive liquid. If you have a conductive liquid and if you would keep this arrangement, then obviously the liquid would short circuit your two electrodes. So you would not be able to measure the capacitance in this case. So it's clear that we need to insulate one of the electrodes. And the easiest way to do this is to insulate the middle electrode in my arrangement, because this has a quite small surface area. This could be, for example, a rod or a wire or a chain. That's well, typically a rod that's insulated from anything that's outside. And then what we are doing is that we have the tank as the electrode, but our liquid is conductive, so it forms the part of the electrode as well. And as we are increasing the liquid level, or changing the liquid level in general, we are basically changing the part again of my capacity C1, which is increasing with increasing liquid level. The advantage of this is that in both cases we will have a linear dependence between C and between the liquid level. Because here we are not changing the distance between the electrodes, it's constant value. We are not changing the material, it's the same liquid, but we are changing the cross-section of our capacitor. So we see that this will give us a very nice linear dependence. That's what we typically want. Now this equation that you see here, this is like a general formula for a capacitor that has planar electrodes. But in case where we have a cylindrical electrode, it looks in a different way. It looks like this. Again, this equation is nothing that you should remember, but here I would like to show you only that it follows the same logic as the capacitance for the planar capacitor. You can see that it depends somehow on the cross sections. You can see here the cross sections in this figure, and this is telling us something about the distance between the electrodes. So here this corresponds to this D, which denoted the distance between the electrodes. So here in this cylindrical capacitor, it's a ratio and then a natural logarithm of that. And then we can see that it depends on the area, which in the case of the cylindrical capacitor, in this case I've denoted as H. So this area times the area of my cylinder here, it's giving me the area of my capacitor of the electrodes. And so we have some material property and then 2 pi times h, which gives us the area. So again, in this formula for capacity, we have the distance between the electrodes, and we have the cross-sectional area. And for those who are interested into how this equation was found, you can see the procedure here. You basically calculate the integral around this circumference, and you can calculate the capacity in this way. Basically, you're looking for changes of voltages at a specific small volume. So at the end, after we calculate all this with those complicated equations, we will get again a linear formula. So we will have that the capacity depends on some constant, I'll call that K1, and this is a constant that is telling me what is the capacity of my connections, what is the capacity of my cables, and so on. And then another constant that will tell me what is the sensitivity, or what is the slope of it. So if you plot this curve, it's going to look like this. This will be H and this will be C, and it's going to look like that. And this will be K1 and the slope will be K2. So again, we have a very nice linear dependence, and it doesn't matter at all if we use a cylindrical electrode or if we use a planar electrode as well. Here is the case of the 2 planar electrodes. So we have the 2 electrodes that are submerged in our liquid, and we will measure the capacitance between those 2 electrodes. So in this case, it's not the tank that's used as one, but we have 2 electrodes submerged in there. This picture is obviously for the case with a non-conductive liquid, so that we don't have a risk that this will be short-circuited by the liquid itself. But again, there's nothing preventing you to insulate 1 or 2 electrodes and use this also in a case of a conductive liquid. And you see that the equation is again exactly the same. Its capacitance has some constant part, this is the C0 here, and then some part that is variable with the liquid level. So for example, here this is the C1, this is the capacity of my liquid here with epsilon R1. So this part is increasing with the increasing value of H, and this part is the part for C2 capacity, and this part is decreasing with the increasing level of my liquid. So C2 is getting smaller, C1 is getting bigger. Typically this is air and this is something like water, for example. So if for air we have epsilon R1 and for water we have epsilon R of 80, then this capacity for the same dimensions will be about 80 times bigger. So we can safely neglect the changes of C2, and we can just take into account the C1. So here are a few examples how this looks like. So this is the cylindrical system. You can see here, well, this is this tube, that's the external electrode, and the rod in the middle, this thing, will be the internal electrode, and when the liquid is changing, liquid level, it will rise inside of the tube as well, and we measure the changes of capacity. So another examples, you can see different versions, think this one is interesting. This one is with the two electrodes, so you submerge two electrodes into the liquid. Here you can see this in this opening we have a view what's actually inside. So again, it's a tube with a rod in the middle, and that's what forms our electrodes. On the top here in this terminal box there will be a circuit that evaluates the changes of capacity and sends this as an output signal, for example a current signal 4 to 20 milliamps. So it's like a quite simple device in principle. It's quite robust, and it can be measuring the continuous liquid level, but as we will see later, it's possible to use it also as point level detection. So it's very universal principle. So what you can expect, you can use it for applications that have aggressive media or even heavy buildup of the material. While aggressive media, it means that you can make the electrodes, for example, from stainless steel, and it will not rust in your application. You can use the silo wall or the tank wall directly as one electrode, and the other electrode could be a rod or a rope or a chain. And it's typically up to quite high temperatures, so up to about 400 centigrades, and also to high pressures. So 100 bar, that's one number just from one manufacturer, but this gives us roughly an idea about the pressures. So quite high temperatures and high pressures are possible with this liquid level meter. Now the next type will be ultrasound, and I will go through this only very briefly because we've seen ultrasound already last week, and it will be very similar also to radar that we're gonna see in a few minutes. So it's clear how the ultrasound works. We send a pulse of ultrasonic energy from a transmitter. Now this travels through the gas that's above the liquid. It will hit the liquid level, it will get reflected, and we are looking for the time difference between the sent and received signal. And this time difference will be proportional to our distance between the sensor and between the liquid level. Of course, it will have some limitations. If we will have obstacles such as internal construction structures in the tank, it may be a problem. If we have foam, then it may be a problem for ultrasound, and then we may not be able to use this ultrasound. But in principle, it's fairly simple to use ultrasonic liquid level meters. There are very small, very inexpensive compared, for example, to radar, and they work quite reliably and well in some specific applications. Here are a few examples how such sensor looks like. So you see here the symbol. It measures from this point the distance, and then it's typically like a stainless steel case or a plastic case, and you mount that above your tank, and you simply measure the liquid level from the top. So it's quite simple to use ultrasound. It is unaffected by some properties of the liquid, such as changes in density or maybe moisture content. It is also unaffected by the changes of dielectric constant, which by this mean epsilon, the permittivity, because we're not evaluating capacity but we're evaluating distance. And it is able to work with lower temperatures typically and lower pressures than the previous principles that we have just seen. So again, some data from some manufacturer, they say 150 centigrades and up to 4 bar pressure. So it's definitely lower pressure than the previous principle, but on the other hand, we can install it above the tank, and it's not in direct contact with our liquid. So ultrasonic sensors are typically installed from top of the tank, and they have the ability to read continuously the liquid level. On the other hand, they do not handle foam very well. So foam will block the propagation of ultrasound, and in those applications it's not suitable to use ultrasound. Now, very similar, and I believe this is the last principle in the continuous reading, is the radar. Now in radar, we install the antenna again above the tank. We transmit a signal, and we measure the reflection. But for radar, we are using radio waves. For ultrasound, it was sound waves which traveled relatively slowly. But radar signals are traveling very quickly. They are traveling with the speed of light. So you may measure that as a time difference. So again, you send some pulse and you receive the echo and you time that. So you basically correlate the time versus length. There is another way that I will discuss in a minute that allows you to overcome the problem that this time might be very, very short. Because here we are working with the speed of light, and we know that speed of light is quite high. So this is the formula that allows you to calculate the distance. C0 is speed of light, time is the time difference, and mu r and mu epsilon r are permeability and permittivity of your medium, of your gas that's above here. So we see that this depends on the properties of the gas and on the speed of light that's there. The time difference that you need to measure is very small. The speed of light is approximately 300 meters per microsecond. So it's obvious that the time that you need to measure will be very small. It will be in the order of few picoseconds that you need to measure if you want to measure this accurately, which might be quite difficult to do with a sufficient level of accuracy. Although it's possible, then there are other ways how this could be improved. And one way how to do this is so-called frequency modulated continuous wave. You will find it also as FMCW. And FMCW is very common in distance measurements and also in liquid level measurements. How does it work? You can see that it's telling us it's a continuous wave. So we are not transmitting a short signal pulse, something like this. That's not what it's doing. But in FMCW, we are transmitting a continuous wave. But what we're doing is that we are continuously changing slightly the frequency of the signal that we are transmitting. So we start from some frequency and we are typically increasing it. So we're sweeping the frequency that we are sending. I have a picture. No, I don't have a picture. No, I don't. But I will draw it. What you can see in a chart. So, for example, if this would be my time, like that, and this would be my frequency of my signal. So what we are doing is that we start at some frequency f0, which is on the beginning of our transmitter band. We are slightly increasing it like that, typically in a linear fashion, up to some maximum frequency, and then we go back to our original one, and then we repeat that sweep. Now this happens very quickly. We just within a fraction of a second we sweep through this whole band. So this is what we are sending. So the signal TX shown in red. Now our signal propagates through open space. From the antenna it goes to our object, and then it gets reflected and we can receive it at our receiving antenna. But this transmission from here to there will take some time. Let's call that delta t. So what we will see here on the receiving side? Well, we will definitely see the same shape. The frequency change will be the same, but there will be some time delay between the signal that I'm sending right now and between the signal that I'm transmitting I'm receiving right now. So time-wise it will look like this. This is my transmitting signal. Here it will drop, and here it will start again like that. So what do we see here? If I am, for example, at this time instant, I see that I have this frequency that I'm transmitting, but I have this frequency that I'm receiving, and this will be my delta t. So in my circuit, in my block diagram, here I'm comparing the frequency that I'm sending right now, so this will be ftx, for example, with the frequency that I'm receiving, so this will be frx. And the trick here, why we are using this FMCW method, is that it's possible to measure very, very accurately small differences in frequency. So we are getting rid of the problem that delta t will be very small. It's like, I would say it's very small. But since we transfer this to comparing the frequencies of our two signals, it's possible to do it very accurately. So we are basically overcoming the problem of measurement of short times, since we are measuring the very small frequency differences. And it's possible to measure frequency difference quite accurately with a very high resolution. So FMCW is used not only in liquid level meters, it is used also in distance meters. If you have a radar distance meter or if you have a laser distance meter, then very often it uses what's called FMCW. Now, what frequencies do we use in liquid level meters? Well, we typically use frequencies in the order of few gigahertz. So it's something like 26 gigahertz, it's like 6 gigahertz, it can be 76 gigahertz. We have really large frequencies. This is how the sensor looks like. So this is the horn antenna, and it's made from stainless steel. This antenna is installed in the tank with this armature, and then of course the whole electronic system is outside from the tank. So the only part that is in contact with your liquid is the antenna itself. So it's very robust, it's very reliable, it sits on top of the tank, and you get the continuous reading. So what can we expect? It will be very good if we have some vapors or dust around our liquid. This will typically have no effect on the measurements. Now the used frequencies are in the order of few gigahertz. So here you see two bands that are typically used for liquid level meters. And since the only part that is in contact with the tank is the antenna, it can work up to high pressures and up to high temperatures. It is also quite accurate, but on the other hand, you imagine that this type of electronic system will be quite complicated, so it will be also quite expensive. We don't have any radar liquid level meter. I wanted to buy some, but the price was about 300,000 Czech crowns, so it is used only in very expensive applications where you really need that kind of accuracy and the properties that are fine in this radar liquid level meter. It can measure also very accurately, so it's something like 1 millimeter accuracy with the distance of a few meters. So that's all about continuous liquid level sensors, and in the remaining few minutes I will show you few more possibilities how to do the measurement as a point measurement. We will see again some principles that are quite similar to the previous ones. So some of them, as the capacitance, can be used for both. This conductivity liquid level meter is also possible to use for both, so it can be either a point level or it could be a continuous reading. It works only with a conductive liquid. If you use it as a continuous meter, you have two electrodes like that, but you measure the conductivity, so you feed in some current, and this current, if you have, for example, a constant voltage, then this current will be proportional to your liquid level, because if you have a higher liquid level, you will have higher conductivity, and if you have a lower liquid level, you will have lower conductivity. So this is the example of the continuous reading. On the right hand side, you see how to do that if it's a limit switch, like a point level. So this would be the setup for lower limit switch. So this will tell me if the tank is empty. If it's empty, then it will be below those two electrodes and it will not connect them together. And this set of electrodes is for the upper limit. So if the liquid level is here or above, it's telling me that the tank is full and I need to start pumping the liquid inside of my tank. So again, this is fairly simple to do, either as a limit switch or a continuous reading sensor. A few examples. Here you can see two level switch. So this would be the reference electrode, this one that is submerged at all times, and you see here that this would be one point and this would be another point where that would actually measure the liquid level in the tank. And so what can you expect? It needs to be working with a conductive liquid. So without the conductive liquid it will not work. As I was already saying multiple times, water, regular water, is conductive slightly, so this will work with regular water, but it may not work with oil or with some distilled water, for example. And the temperatures are about 150 centigrades and pressures up to around 25 bar. Again, those are just some numbers from one type of the sensor, the one that you see on the picture here. But you may find a little bit different values for different manufacturers. Few more examples how that may look like. So it may have different number of electrodes. So here we can see 1, 2, 3, 4 electrodes, I believe, are there. Here again we have 4 electrodes, and here I don't know, it's hidden in this ceramic cover, but probably maybe 2 or 3 electrodes will be there as well. Okay, and the very last one will be the vibrating fork. So this is quite different from all the other principles that we've seen so far, because this vibrating fork will work only as a point level switch. All the previous examples were continuous, but they could be made also as point level, including the conductivity meter, but this vibrating fork will work only as a point level meter. Now there is a very nice video on this link, so I recommend you to take a look on that. It explains quite well how this principle works. A vibrating fork. This is the fork that is submerged into the liquid, and we made it vibrate with some typically piezoelectronic exciter. So it will move back and forth like that. It is clear that the vibration will be different if the fork is in a liquid or if it is in the air. If it's in the air, then it will vibrate freely. We will not need to put so much energy to make it vibrate. If we submerge that into the liquid, then even the vibrations may stop completely. So we have a piezo exciter that makes it vibrate, and we have a detector that detects if we have vibrations and what is the amplitude of my vibration. You can see here on this picture that this is really like a point level detector. So the sensor on the bottom is telling me, okay, the tank is not empty, and the sensor on the top is telling me the tank is full or it is not full. So I cannot tell if the liquid level is like here, or if it's like there, or if it's like there. I can only tell that the tank is empty or not, or if it's full or not. Here you can see a similar explanation of the internal workings. So this is the part that vibrates back and forth. In this case they are doing this with an electromagnet, so they resonating this part, and they are detecting the amplitude, and if this is, for example, a solid, or it may be even liquid, then the amplitude will change, or the vibrations will stop completely, and this is detected in the electronic circuit. So this vibrating fork principle, or it's called in general, it's called vibronic. It may be used for liquids, and it may be also for solids. That's what they say here on the video as well. Here is how this sensor looks like. Well, I have few of them in school labs, but unfortunately we cannot see them in person right now. Here, this is the vibrating fork, or you can see it here as well. It's typically made from stainless steel, because it's robust, it will not rust. And here this fork vibrates like this, and this fork vibrates like that, and we detect the vibrations. If it's submerged in a liquid or in solid, then it will stop vibrating, and we can detect that. So you can see also how this is mounted in the tank wall. So it's mounted from the side here with this thread, and this sticks into liquid, and this is outside of your tank. Here the same, this is the thread, and this is outside of your tank. It can be also hanging from the top of your tank, so then it looks like this. You can see either cable or a stainless steel rod, and at the ends you have those two forks, and they're vibrating, so this moves back and forth, and you detect again if the vibration stops or if it changes the amplitude. So it's just like very simple in mechanical terms. It is also very reliable. You can see that basically the only moving part is the very slight vibration of this, which is very small, and there's no problem with that. So what can you expect? Well, this works also if you have air bubbles and if you have foam. It can also detect the solids underwater. So for example, if you have a tank where you expect sediments, then it may look like this. You may have a tank. Let's say this will be my tank, like that. I expect that I will have sediments here, and this will be my liquid level. So water with some dirt at the bottom. So I can have one sensor that measures the liquid level, like this, either vibronic, or it could be ultrasound, for example, like that, or radar. And then I can have another sensor that is submerged in this area with a vibrating fork in there. And if this sits in the sediments, then I have info, okay, now there is sediments, and I have to properly clean and drain the tank from this sediment. So this principle can detect also underwater the presence of some solids. It is applicable also if you have bubbles and foam, because it's under that liquid level and you basically don't care. It is only a point level switch, so it will not give you a continuous info. It is able to measure all pumpable liquids up to very high viscosities, and it doesn't care basically about turbulence, foam, or bubbles. They do not impair the operation. Here I forgot to put the links, so I will add that and I will upload the presentation in Moodle. This should be some more comparison of the principles of the liquid level meters. So that's all for the group of sensors, and next week we will start about the signals, and then we'll switch to the methods of sensing.